Hello boys and girls. So this video comes in 3 parts. The first part is a little bit ranty. I had some ideas and thoughts regarding the medium of these videos, as I sometimes do, and in particular about LLMs, how to integrate them, and I had some ideas that, just came up as I was doing my thing, and I quite liked them, and I would like your feedback on them. So the first 5 minutes I will talk a little bit about what came to me. Then we will, as we often do, go through some Python script. I will explain some things. They are related to the correlation between two simple random variables, and you might learn something there. This is very basic. It's related to my autocorrelation video that I did 1-2 months ago. It's even simpler, but I think you don't usually have that, especially with code in Probability 101, and you will probably learn something if you are not too deep into probability theory there. And it helped me, and you have some starting point to code your own stuff there. And then we will talk about the thing that actually started the idea yesterday that I had to make this video, some mathematical results related to covariances that yesterday I didn't actually knew myself. I ran into them and I found them interesting, and that's why I present them. And that's actually where my story begins. So the next 5 minutes will be a little bit of meta, but they are quite of interest to me, and I would like your feedback. So yesterday I was reading this book from the library. I did not know this before. It is like fairly thick stochastics book, and very on the formal measure theory side of things. So there is surprisingly little like examples, and even it doesn't even bother listing too many distributions and these kind of things. However, this is a very nice book. I found it very funnily written. The preface and text so far what I wrote, I had like 1 day to look at it, but I quite like it. However, this video is not a review of the book. I'm just saying it seems like a good book. But so I was skimming it basically, and on page 80, it gives some examples of some standard distributions, and it talks about Bernoulli trials, and it gives you some results, some expectations. And I was like, okay, interesting. The author seems to make some more restriction on this probabilistic situation than necessary. And I was lazy, and I was plugging into ChatGPT, hey, if this and this, and I made it more general than what is presented on this book page there. What is the expectation value of blah, blah, blah? Okay, and I get the result. And then, I was spinning further. I'm thinking of, if I have 2 random variables that are similar, but also a little bit different in this and that regard, what is actually the covariance? It was not in this book. And I plugged it in, I got the result, and I was actually surprised about the result, which prompted me to, hey, make a video about this and discuss this. This is quite interesting. And I started first to refine a little bit the prompt to get more information out of this and to understand it a little bit better. And I was like, okay, if I make a video about it, as so often, I will make a script and validate this empirically. Basically, this sort of law of large numbers validation that I sometimes did in the past as well. And I was writing the script, and then I added more ideas, thoughts to it. I was conversing in the same chat where I did talk with the LLM. And then it came to me, and this is the point. I was like, hey, usually in these videos, I go to my wiki, might know it with the blue background, and I present some text that I want to go through and explain some things based on it in LaTeX. And what if instead of actually writing the script myself, I spent the same time on tweaking the prompt for the ChatGPT thinking model? And you can switch out any LLM here. And I provide in the video not the script, which probably not too many people look at. I know some people sometimes look at the Python code, but maybe not the script for the text that I present. But instead, I do not give you a script, and I don't even give myself a script, but I actually prepare a prompt and this is, above and below this code, there is basically a vast extension, a very refined extension of the conversation I had with this thing. And this is what I will give you in the gist on GitHub, which you can click in the link below. And here I will plug this into this thinking model, and it will work for like 1 to 4 minutes or so now. And I will discuss the Python code, and then we come back, and I will just present to you these results based on whatever ChatGPT puts out there. I have refined, like I have done this now 20 or 30 times. I refined the text, what I really want. And what I like about it is I have noticed just in this like 10, 15 iterations of getting the same output, what you usually don't do, usually you do not plug the same like large text into it over and over. Especially if it's like some very dry stuff where there's usually a right answer and it gets it right the first time anyway. But I noticed how my specifications, for example, of mathematical notations, you see here some style guides, use these vectors, use bold notation and so on, how that's improved over time. And I'm glad because now I have this and will use it the next time as well. And my hope is that making this video, you get an idea of what I do there, and maybe you have even feedback, hey, do this and that. And this might be actually a contribution also then to the medium, right? We are interacting with this LLMs and agents, and I know that in the coding domain, people share, how they want to have their code formatted and this kind of guides and how they want to tune the agent, and this can be done with just math and physics as well. I mean, clearly as we see here, and I'm sure people also do have their standard inputs, but usually probably don't really share them in this domain yet. And I'm going a step in this direction, and I think this might be worth trying and working this direction. Please tell me in the comments what you think about this. Okay, and with that said, let's jump into the second part, which is discussing this Python code. Okay, so what the code will do is basically the encoding of a 2 random variable situation. And I will sample from this, and I will talk a little bit about the covariances and the conditional probabilities and these kind of things. The special thing about it is that I'm not talking about independent random variables. Like too often you have this IED, independent and also identically distributed often if it's a sequence random variables. But in this case, I purposely want to have the more general case, which is the case in which you then which helps you understand correlations better as well, right? So this is particularly about the dependent 2 random variables. It's only 2, so it's in a way simpler than the autocorrelation video that I did 1-2 months ago. But in a second we will discuss the code and what it does. Before that, give me a minute. I will talk about the simpler thing that I do not implement here, or at least where this is just a very special, simpler special case. I want to just in words describe the independent situation. And now you have to listen a little bit because I will use some variable names and you have to follow in your head. But so basically what I do not do here is just sample 2 random variables independently. So in the text, I will scroll up, but you do not read this. Just pointing it out that the LLM will also notice. So we will have 2 random variables, capital X lowercase a and capital X lowercase b. So a, b are the indices for the first and the second random variable. And each, like this is on my hands, this is the xa and this is the xb. And both of these random variables take values in a codomain with 2 values. So we, without loss of generality, like just to name them, I will call them the success outcome and the failure outcome. The first outcome is the success outcome. The second outcome is the failure outcome. These are just names. And the second random variable will also have a success outcome. It does not have to be the same value, numerical value or whatever. This is just a label. The B success and the B failure and the A success and the A failure. But this is the situation. We have 2 random variables and they each can have one of 2 values if you sample them. Now, if you sample them together, the independent situation arises if you do the following sample process, right? So let's say the random variable xa with probability pa results in success, and with probability 1 minus pa results in a failure. And similarly, the second random variable xb with probability pb, which can be a different one from the first, results in a success and otherwise failure, right? So here you have two p's, pa and pb for xa and xb, such that success happens. And what you can do is, you do like what we will do here 1,000,000 times. I can even do this 10 million times. Do the following: we sample for xa, and then we also sample for xb. We get some outcomes. For example, there are 4 outcomes basically: success, 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 failure, failure, success, failure, failure. And then we plug them into a pair, and we record, oh, this is what we sampled from A and B, and then we go to the next sample and repeat the process. Okay, if we do this, then fairly trivially, the marginal probability distributions, right? If you just look at the first component at xa, I do this process where I sample all these pairs, and then nonetheless I throw away whatever b was. I just look at xa. Then by the law of large numbers, I will find that roughly here in this case, if PA is 60%, 60% of these values will be successes and 40% will be failures. And similarly, if I look just at the second component, like here in this case, I use, let's go up to 47%. If I do this and look just at the second component, 47% of them will be successes and the other will be failures. So the marginal probabilities for both are some Bernoulli trial with some outcome governed by one number. But this code that we will discuss is more complicated insofar as it is designed in a way that it samples more generically from a joint probability distribution. Right? There is basically one scalar more. So I can specify this delta success, which bumps up the chance of having a pair with 2 successes. So it's not just the product of the marginals, but I actually have I correlate these things such that this happens more often. But nonetheless, the whole distribution is designed, like in the code, this is still designed such that if, the code computes probabilities that are actually used for this joint distribution, such that if I later look at the marginal probabilities, like just the first component or just the second component, this is still a Bernoulli process with the probabilities that I put as an input, right? So unlike the independent case, there's basically a spectrum of dependent joint probability distributions. They're like a spectrum of parameterizes these, such that the marginal probabilities are still Bernoulli trials, not normal Bernoulli trials. You could not if you have just access to the first component, you could not know that there's any correlation with the second, and you cannot know the p, and you cannot know how bumped up the success cases. I mean, that's sort of clear, but so this is what the code does. It just defines a generic joint probability distribution such that the marginals are still Bernoulli trials, but it parameterizes them not by the actual p's that are used, but by these 3 values, the marginals and this correlation factor, the excess probability as I call it here. Okay, and so the implementation is really simple. I define the probability of both being success as whatever, like this is basically just the definition of this delta. What the probability would be if they were independent, and then I add this bump. So this, and this is basically just the definition of this delta. And then the probability for XA being success and XB being failure is the marginal for XA being success, right? The marginal takes whatever the second component is, and then subtracts the situations where both are successes, right? So success failure equals marginal, which ignores the second component, minus success. Yeah, and similar for failure success. And then the last component is just determined by normalization, because they have to be probabilities. Okay, and then I do some validation. There is certain bounds around the delta, such that this makes sense. So you can break out of this. You can take a delta which is so wrong, so to speak, that the marginals are not Bernoulli trials anymore, so that breaks down. I will not talk about the theory here, but it basically says, roughly speaking, the probability of having success cannot be higher than the marginal probability for the first component, or for the maximal component, just to be successes, right? So the marginal forgets information, and so this must be always more or equal to both being successes. Okay, I mean, you can think about this, but this is basically some fairly simple theory. This is just some sanity restriction. Okay, and then in the code I log what 7 values I use. The 3 I use for the parameterization, and then the 4 that come out. And then if I run this in the main body here, where I use this distribution, what I do is I take my configuration values, I get my 4 probabilities, and then I sample it 10 million times. And then I look at the first component and second component, the XAs and XBs. And these are defined such that these hold, they are true if they're successes in the first components, or otherwise false, right? So this, the NumPy here casts it to true or false. And yeah, and then I can compute the rate, how many are of the first are successes, how many of the second are successes, jointly, how many are success. And then I can compute conditional probabilities, right? Given that the first component is success, what is the likelihood that the second is also a success? And this is tweaked by me having bumped it with this delta. And then I look at the covariance. So let me run this script here. It produces some of these outputs. So for example, here it starts out with, these are the marginals I defined, 60%, 47%, and then I bump it by 14%, the likelihood that there is success. Here is the probabilities that are computed from that. It turns out then that it's super unlikely with these numbers here that the first is a failure, but the second one is a success, right? Because the marginal here for the first being success is high, the marginal for the second being success is lower, and then it comes out in a way that because success is so high that the pair case failure success is very rare. But I mean, this is whatever. This is just how it comes out. And then I plot the first 27 result. Let me actually check if there is any failure success case here. Yeah, there's even a failure success case. So this is fairly rare. This is like 5% chance of encountering one of those. And then I have all the probabilities specified by hand in the class, and then I can compare empirically what I sampled with what I set. Interesting is this, in this case for this video, with the covariance. So I compute also the covariance here with the NumPy code np-cov of these two success random variables, and this value, the value cov-mat, the AB value, comes out as 0.1399, so 0.14. And one of the theorems that we will see in the last section, in the third section of this video, is that it just so happens that this covariance matrix actually equals this bump factor of success. We will see this in this as a theorem there, but this comes out, and I actually validate this empirically, and you see there's a lot of zeros, so this checks out by the law of large numbers. There will be some variance from that, but this goes against 0. Okay, so this is the code. You can play with this Python code. You have now the ability to tweak this around. I could set this to 30 and rerun this. There are some, it will fail if I break this Freche bounds, if this is such, if I choose accidentally the probability such that it does not check out with actually being a joint distribution, which results in Bernoulli trials as marginals. But you can tweak this, and you have some code, and now you are capable of doing this very simple 2 random variable to 2 output values, but sample them not independently but dependently. There is a covariance. The covariance in this case basically has the impact that I do this here. So if I fix XA being success, if I just look at the cases where the first component is a success case, then what is the chance of the second component also be a success case? This comes out to be 93% here, right? And if you compare this with the marginal of just the second component being success, this is almost double as high if the first is success. So knowing that the first component is a success, it gives you a lot of information about the second also being success, right? Because this is because I chose this bump factor to be non-zero. Right? I could put this to 0, then the correlation will go. I mean, I can do this here. Let me put this delta factor to 0 and run this. Then P, the second component being success, when the first component is a success, is basically 47%, and in this case the same as if I just look at the marginal. So in this case, because I turned off this bump factor of double success, I get no information from knowing that the first component is okay. Now I hope this makes sense, and you have this tool, the script to play around with this and understand this a little bit better. Okay, so I plug this script with all this information into ChatGPT. I will load this again here, and I have not looked at the output yet. We can look at this together. I think it thinks so. We might have to wait 1-2 seconds. The connection was lost, but it goes through all of this. And so I will let this just generate what it generates. I have seen this basically now 20 times. I know roughly what it is. I will talk through the text. And you can take the text and repeat this for yourself in your chat of preference. And maybe you reflect on what you think about my prompt. Okay. It does not seem to compute. Maybe it's because I have a bunch of stuff running on my laptop. But let me repeat. Okay, now it goes into thinking. Yeah, I'm sorry, you might have to wait with me for a minute. We can see what it thinks about. But yeah, to spoiler you, what I do in this prompt is I first look at the same sort of scenario that I just described, except in the first part, I do not restrict the random variables, the two random variables, to have take values in just sets of 2 elements, but I keep this open. I map into some finite number of outcomes. And what I'm interested in for this finite situation is how the covariance matrix generally looks like. The covariance matrix, and I even allow for like some functions on the state space. We will get a nice expression which depends to a good extent on this correlation factor. So even in a general case, this correlation plays into the covariance. And then the thing I saw, which I was so surprised about, which prompted me to make the video, is that if you then go to the Bernoulli case, where the correlation, this bump factor, this SS bump factor, this bump chance of having success, this then the covariance. It turns out that all the factors, like all the aspects which depend on the probabilities that it shows PA and PB, actually factor out. And so this becomes a very clean expression which just has a one factor depending on the whatever function you use on the event space, what you're interested in, and then this delta factor, this bump factor. This was what I found surprising. So basically, if you look at the ratio of two covariances, even for different functions, it will not depend on these probabilities, which I found nice. Okay. And then at the end of the video, I will also show you some derived random variables defined in terms of XA and XB. And we will have a situation that I can force where, despite the random variables being highly dependent, like in some cases 100% implying each other's outcomes, you still can force the covariance matrix to be 0, meaning just looking at the covariance, which basically determines the linear dependencies but not other dependencies, you can still get the dependent outcomes. But okay, we will see this in a second. Damn, that takes forever. I don't know if this is related to me doing the video here. Because I think when I ran this before, I mean, this is the thinking mode, GPT-5 thinking mode, so this is the paid model basically. It took sometimes like 3 minutes or so, but I think we are now over this time. But okay. Yeah, sorry for that. Okay, so it starts. Okay, so the third part of this video begins. So again, we have these two random variables. K is the index, the first or the second, A or B. These are my names. And they take values in finite sets. The first set can have NK and NA elements. The other can NB elements. And so, he talks about setting up the joint probability distribution. This is very general. And I isolate from this the matrix of the probability entries, this delta, similar to what I had with the Bernoulli case, except we're not in the Bernoulli case yet. This is a full matrix that determines this correlation. And it discusses here, I asked it to do this feasibility bound so that we get the marginals. Again, I will not talk about this here in this video, but there's some boundaries that for this to make sense as a joint distribution. Okay, and now I'm interested in computing these sort of covariance. This is the covariance, right? The expectation of the delta to the expected value, blah, blah, blah. And we take the XA and the XB, we apply any function on it. I mean, the domain of these functions are just one of two values, success or failure, right? But still, there are two functions, FA the first function applied to the first random variable, the second function applied to the second random variable. And then it turns out that the covariance actually takes a nice form. It is basically purely defined in the correlation part, right? This delta. It does not depend on this simple product part, this PAs and PBs part, which is nice. It's like has a simple form. I will not discuss this further, but just do you see what happens if I don't make any like simplification assumptions? And then I pass on to the Bernoulli situation where we are only reduced to two values as in my script. This matrix, the correlation part matrix, is basically now governed by just this one value. ChatGPT chose to call it small delta, and it's basically this symmetric matrix with 1 minus 1 minus 1 1 times this delta. And so if I now compute already above we had that the covariance depends on this delta matrix, and then on this nice delta f's, and these are some differences of the function output values. Okay, you can read this on your own, but basically these are objects which only depend on the functions, not on the probabilities themselves. It's just the output on the functions. And so this is the result that I saw. What is nice, the covariance of this Bernoulli process that they discuss also in the code. If I take these outputs and map away the success and failure to anything else with these f's, can be different f's, the covariance still has this nice form where it's just a product of three expressions. This delta, which is the correlation part in my joint probability distribution, like this is this one scalar. This determines how more likely this double success is. And then this factor that only depends on the values of the function. This is very simple, and the funny thing is then if you take this covariance and divide two covariances again by each other, it means that this does not depend anymore on any of the probability stuff, which I found interesting. This was what I saw when I tapped this into ChatGPT when this was not in this book, and I was like, what? This is very strange. At first I thought this is so simple. I mean, it makes sense insofar as the whole situation is determined by so few parameters, but I found this interesting. Okay, this is the basically result that prompted this. And then you get other simple expressions for the correlations and the variances. These are something I will not discuss this into too much detail, but also all nice and very simple formulas, given the fact that I have left so much open still. Okay, and so finally, this part is new. If you take the situation that we just had, and we assume that XA and XB actually take values in the same codomain. So this is more like a coin flip where you have two coin flips and the outcome of the first can be heads or tails, and the outcome of the second can also be heads or tails, except for the second random variable, the probabilities, how often heads happens, is still not determined. Like it's still PB, it's still open, it's still whatever you want to do. So you can still have two. Basically, you flip two fake like unfair coins. You have unfair coin A, unfair coin B. You flip them. You get success with a certain rate, both unfair, but they are still counted as just heads or just tails. It does not matter in the output that they came from different random variables. The random variables just determine how often heads comes up, but not the fact that heads and tails are the only two values, success or failure, that can come up. Okay. So we have these two output values, and we assume that they are like elements of a ring, the reals or whatever, so we can add or subtract them. Okay. And now we define two other random variables, C, which is the sum of the outputs, right? So if heads is 1 and tails is 0, then C is the sum of whatever comes out in both of these coin flips, and D is the subtraction. Okay. And now the important thing is that this D random variable has the feature that if both unfair conflicts come up with the same output, for example, if both are heads, if both are successes, or if both are tails, if both are failures, then this will always be 0. So this is not an injective map, right? So in both cases, this is 0. And so it then turns out that, I tell it, hey, please define these derived the random variables, compute what the possible outputs are. And then if I look at the conditional probability of the sum being this value, basically, again, if I use 0s and 1 for this representation of heads and tails, if I say the chance of the sum of the coin flips being 1, given I know the difference of them, what then comes out is that, maybe this is a little bit too much information here, but basically, if I know that the difference of the outputs is 0, which implies that they actually came out to be the same, right? If heads minus heads is 0, tails minus tails is 0, but if they are different, then it would not be 0. So if I know the difference, then I also know that if I know, for example, that they came out the same, then I know that the value, the sum cannot be 1, right? Because if they're both 0, if they're both 0, if they're both tails, then the sum to 0. If they are both heads, if they're both 1, then the sum to 2. So I know it can never be 1. So I have the situation that if conditioned on the d random variable being 0, C can never be this mix of two different outputs. I hope this was not too confusing here, but I have the situation where basically one output determines the other in certain situations 100%. But nonetheless, the covariance is such that if I choose the probabilities for if I choose the p's for the first and the second coin flip in a certain way, right? There's various ways in which I can choose this piece. Then I can force it that the covariance of these derived random variables is 0. So I have the situation that the covariance is 0 despite them still being very dependent. This is a sort of standard example, except maybe I should have made simpler assumptions there. I on purpose I did not map to 0 and 1. I wanted to have it generic and say, hey, even in this generic case, this phenomenon still happens there. But you can play with this this prompt and play through it. The main point is just that covariance being 0 does not mean you have independent processes. These independent derived random variables are still highly, people say, oh, they are highly correlated, but this is actually the wrong language. By covariance being 0, they are actually uncorrelated, but they are still dependent. So it's important to know the difference between these words. Words have meaning. Okay, so and then there's some concluding remarks. I don't want to dwell on this too much anymore. But yeah, so this was the video. I hope you learned something and you have now the tools. You have both this starting point to talk with ChatGPT about independence, and this might be one of the simplest cases where you can actually study what happens with covariance versus independence. And you have this Python script to actually sample stuff and look at this, and you can manipulate this. If you do this and play with this, report back what you think of the script and the prompt and how you would change it. By the time you report back and see this video, you might have, you might be in the AI future, and I have much more better ideas on how to prompt these things better. But it's a process, and so I will stop here under 40 minutes. I hope you like this, and I wish you a pleasant Sunday night.